When the 2001 Bhuj earthquake struck Gujarat, thousands of concrete structures were reduced to rubble in seconds. The ground itself failed. To prevent this level of structural collapse, the Indian engineering industry relies on IS 1893, Part 1, Criteria for Earthquake-Resistant Design. But in practice, this code is often treated as a bureaucratic checklist. Engineers plug numbers into tables and extract coefficients without questioning the physics behind them. IS 1893 is a rigorous physical model. It translates the transient dynamics of seismic waves into the mechanics of granular soil. To understand how this model works, we have to deconstruct the geotechnical workflow. We will trace the logic from macroscopic regional hazard zones down to microscopic pore pressure limits. You can find 5 interactive calculators for seismic zones, soil types, bearing pressure, liquefaction, and field tests linked in the description below. Designing structures based on the code's physics ensures foundations remain stable under actual seismic loads. The baseline seismic hazard across India is established by the seismic zone map, which divides the active fault regions into zones 2 through 5. This equation determines the design horizontal seismic coefficient, or AH. It dictates the lateral force a structure must withstand, and it breaks down into 3 distinct modular variables. The first variable is the zone factor, Z. This represents the maximum considered earthquake, the worst-case shaking expected for a region. The code mandates dividing Z by 2 to design for the design basis earthquake, relying on a building's ductility to absorb the rest. The third variable, SA over G, is the spectral acceleration. This factor is entirely dependent on local soil stratigraphy, classified as Type 1 hard rock, Type 2 medium soil, or Type 3 soft soil. This chart shows the spectral acceleration for each soil type. As seismic waves move from bedrock into softer, unconsolidated sediment, their amplitude increases. Softer soils physically magnify the seismic waves. Notice that the spectral plateau for Type 3 soft soil remains at maximum acceleration up to a natural period of 0.67 seconds, whereas the plateau for hard rock drops off much earlier. Consequently, buildings sitting on soft soil absorb maximum lateral forces over a much wider range of natural frequencies. The zone factor sets the regional threat, but the local soil profile governs the final structural demand, often acting as a primary force multiplier. This brings us to a paradox in IS 1893 Table 1. During an earthquake, the code permits up to a 50% increase in allowable bearing pressure for Type A hard soils and a 25% increase for Type B. Does the soil beneath the footing suddenly gain shear strength while the ground is shaking? Under static loading, a foundation carries permanent dead loads. Because the load is constant, any excess stress will accumulate over years, leading to severe, permanent settlement. Seismic forces, however, are transient. They are short-lived load spikes that last only a few seconds to a couple of minutes. Granular soils exhibit higher resistance to brief loading than to sustained loads. The soil rebounds elastically, which is why the code permits a bearing pressure increase. But there is a critical exception. Type C soft soils receive a 0% allowance increase. Soft clays and silts undergo excessive instantaneous settlement, regardless of load duration. Increasing pressure on these soils during a transient event causes permanent deformation. The code recognizes that transient loads do not produce cumulative settlement. The rules of physics still apply. If the soil is too weak to resist even a brief spike, the foundation will fail. In seismic zones 3, 4, and 5, granular soils face an even more severe failure mode, liquefaction. Liquefaction is a process where loose, saturated, cohesionless soils lose their shear strength during an earthquake. When this happens, the ground completely loses its bearing capacity. Entire street levels drop into deep fissures, and structures sink directly into the earth. At the microscopic level, the cyclic loading from seismic waves causes excess pore water pressure to build up between the soil particles. When that excess pore pressure exactly equals the initial effective vertical stress, the weight of the soil column above it, the grains lose physical contact. The shear strength drops to 0, and the soil behaves like a liquid. To predict this phase change, IS 1893 Annex F outlines a simplified stress-based procedure. This procedure begins by calculating the cyclic stress ratio, or CSR. This represents the seismic demand, exactly how violently the earthquake will shake a specific column of soil. That demand is compared against the cyclic resistance ratio, or CRR. This is the soil's inherent capacity to resist that specific intensity of shaking without liquefying. Liquefaction is a strict, deterministic balancing act between seismic demand and geotechnical capacity. But how do you measure the resistance capacity of a soil layer when taking an undisturbed sample of loose sand would destroy its fragile structure? IS 1893 mandates 3 in-situ technique methods to gather this capacity data directly from the ground: the standard penetration test, the cone penetration test, and shear wave velocity measurements. The most widely used method in Indian practice is the standard penetration test, or SPT. However, the raw blow counts recorded in the field are mathematically useless. They must be corrected for equipment energy efficiency, normalizing to a 60% energy ratio, and for effective overburden stress. The final correction step adjusts the normalized blow count for fines content. Fines content is the percentage of soil by weight passing a 75-micron sieve. This equation yields the clean sand equivalent resistance. This is where engineers relying on outdated documents fall into a dangerous trap regarding highly silty soils with a fines content of 35% or greater. The original 2016 printing of the code contained a severe typographic error. September 2017's Amendment No. 1 corrected the alpha coefficient for these soils from 0.5 to a flat 5. Using the unamended alpha value results in a 10-fold error when calculating the soil's resistance capacity. While SPT provides discrete data points, the cone penetration test offers a continuous stratigraphy profile, and shear wave velocity is essential for gravelly soils where penetration tools face refusal. Field data is meaningless unless it is rigorously corrected to reflect the true physical state of the ground. The workflow culminates in the factor of safety, dividing soil capacity by earthquake demand. If it drops below 1.0, demand wins, and the soil liquefies. The code targets 1.2 or higher to ensure resistance with minimal deformation. When the calculations predict failure, engineers must implement mitigation strategies. This means densifying the soil through methods like vibrocompaction or bypassing the liquefiable layer entirely using deep pile foundations anchored in competent strata. You can access the interactive calculators and step-by-step guides for executing these exact procedures in the link below. IS 1893 is a translation of transient physics and effective stress mechanics into actionable mathematics. By understanding the physical forces driving those equations, engineers design systems that actually survive reality.